This recording will cover Primary Math 3, Intensive Practice, page 5 through 11, the word problems in this first section. Starting with number 1, we're just working on making sure we can really handle different ways of calling different names for the numbers. If we have 36 $100 bills, that's $3,600. We talk about 3,600, that's not so unusual, but 500 $10 bills means you have 500 in the tens place, and so this is how we write 500 tens. So the question, of course, is how much money is it total, and when you combine these, you have $8,600 from the $100 bills and the $10 bills that were given. Number 2, Sean collected 1,892 marbles, and then Gary collected more than him by 20 hundreds. So of course, if you collected more, you're going to add those numbers. 20 hundreds is the same thing as 2,000. So Gary collected 3,892 marbles for himself. Certainly starting with kind of an easy set of problems, but that's good. We're getting our feet wet with all of the new kinds of problems. At a football game, there's 1,688 spectators. It tells us that 50 tens of them were women and children. So the women and children are in one group and the men are in another group. If there are 50 tens, then that's the same thing as 500. And I hope when you see that you know, if you're trying to find out how many men there are, that if you took the 500s away from the 600s, that there would be 100 left over. And so there are 1,188 men at the football game. Help your child get in the habit of putting units on their answers, and even putting a box around answers is a great habit because it helps you to find the answers as problems get more complicated. Number 4, factory workers are packing candy into big cartons. We're trying to find how many pieces of candy are in one carton. I know there's 5 bags that have 1,000 pieces each. I know there's 7 bags that have 100 pieces each. There are 8 bags that have 10 pieces each. Again, not a difficult problem. 5,780 pieces of candy in the carton. At the end of a day, a bank teller counts the money. She has received 3 $1,000 bills, 9 $100 bills, and 24 $10 bills. If you have 24 tens, it looks like that. 15 $1 bills. And when you add these together, remember, we would always want to try and practice doing mental math. We always want to do math from left to right. So when I'm adding the thousands, I'm looking at the hundreds, and I see that there is a 10 to be made in the hundreds, so I'm going to make my thousands a 4,000. The 9 and the 1 go together and make a 10, and there's 1 left in the hundreds spot. Now when I look at the hundreds, there's certainly not enough tens to make another 100 out of it, so that 100 that I had left over when I made the 10 and moved it out, that 100 is left, and then there's 5 tens and 5 1s, so the teller had $4,155 that she counted or collected over the course of the day. Number 6. We're given that there are 3 rectangles that stand for 300, and so your children will be able to intuitively figure out, if they have to be the same, and they do, that each of the rectangles then is worth 100. Now, if they are not comfortable yet realizing that a rectangle with a diagonal drawn through it divides that rectangle into 2 triangles that are equal, then that's an important part to know for this also. So make sure they have that knowledge clear. But what we find when they're supposed to find the value of the figure that I copied in or drew here, these are each 100, and then each of these three would then be worth 50 because they're half of 100. And so 3 50s is 150 total for those parts, and the entire amount that the blocks are equal is 450 because we have 300 plus the 150 from the 3 halves is equal to 450. Now this is an unusual problem because there are no units. The answer is a number. The answer is it's worth 450. Number 7 has some numbers to draw. The problem has this pattern of numbers, and we're supposed to find the ones that are missing at the very end on the far right side. We don't know what the pattern is. We wouldn't know how to guess, so we just have to explore and find out. You could have to add, subtract, multiply, or divide to get from one number to another. It might be that the vertical numbers are related or the horizontal numbers are related, but remember to think simply. Start out the easy way and check and find out. And what you realize is that when you make a jump from one number to the next, every time you do that, it is a jump of 9. 835 plus 9 is 844. 844 plus 9 is 853. So to find our missing number, we're just going to add 9 to the previous number on the top and to the previous number on the bottom and get 276 for the top number and 872 for the bottom number. Number 8, Thomas is going to join a line to collect tickets. We know that from the first person in line, here's person number 1, all the way down to Thomas, here's Thomas. Thomas is the 100th person in line. But we also know that he's 100th from the end of the line. We want to know how many people are in the line. Now, the only tricky part about this is realizing that if he's the 100th person in line, there are 99 people in front of him and he's the 100th. It works the same way this way. If he's the 100th from the back, there are 99 people behind him. It's a very quick answer to say, oh, there's 200 people in line, but that would double count Thomas. In fact, there's 199 people in line, and stopping and realizing when you're counting things like this, if something is being double counted or missed altogether is a good thing to realize in kind of a number theory way. So actually his 199 people are in that line. Number 9, Mrs. Lathan baked 3,457 cookies. She packed some of them in large bags with 100 cookies each. She packed some of them in small bags of $10 or $10 cookies each. So the question is, if you start with 3,457 cookies, how many large bags and how many small bags do you pack? And then are there cookies that get left unpacked? Well, again, we want to break this number down, and realizing that 3,457 has at its core 34 hundreds is a very helpful thing to realize. That tells me the fact that I have 3,400 tells me that I'm going to have 34 large bags of 100. And then I have the number 57. If I break that down into a 50 and a 7, what I can find out from that is that the 50 tells me very clearly that I'm going to have 5 bags of 10. And then this 7 is what's left over. Those 7 don't fit into a bag, so I have 7 cookies that are unpacked. And it's not so much about doing the math as it is about reading the number in the correct way to be able to state the answer from that. Number 10. A shopkeeper sells a lot of marbles. The shopkeeper has boxes of marbles that have 100 marbles in each, and they have bags of marbles. Each bag has 10 marbles in it. So we're told that he sells 12 boxes and he sells 338 bags. I hope you're beginning to do this mentally, that 12 boxes is 1,200 or 1,200. 338 bags is 338 tens, which is 3,380. And the question, of course, is how many marbles were sold that month? The total marbles sold were 4,580 marbles were sold. Again, always put a unit or an explanation of what your answer means. 4,580 is an incomplete answer. Let's go ahead and talk about the challenging problems. The next three of them are the challenge problems. Always worth doing, very often a little bit of a different kind of a problem to solve. This one says I'm a 3-digit number and all 3 of my digits add up to 9. The tens digit is twice the hundreds digit. The ones digit is 3 times the tens digit, and there are no zeros. Now, when you have a 3-digit number, you can never have a 0 in front because that is in fact the number 12. That's a 2-digit number. Even if you write it like this, it's still a 2-digit number. So we know for sure that the 0 can't be in front anyway in the hundreds place, but we also know there are no digits or no zeros at all. Now, if you read this a couple of times, you'll begin to notice that everything is taken off of the hundreds digit, and so the tens digit is twice the hundreds digit. So if I say the hundreds digit is 1, I can make the tens digit 2. The ones digit is 3 times the tens digit, so that becomes a 3. And that's one option. This is a possibility. As it turns out, if you add these numbers together, 1 plus 2 plus 3, I'm sorry, I did it wrong, didn't I? The ones digit is not 3 times the hundreds digit. The ones digit is 3 times the tens digit. So that would be a 6. And that's why when you add them all together, you do in fact get 9. So 126 is the number we're looking for. I think it's important to notice this as well. If I continued, I just happened to try the 1 first. I knew I couldn't put 0 down, so I tried a 1. If I tried to put a 2 in the first place, and I doubled it for the tens place, and then I'm supposed to multiply the 4 times 3 to get the ones digit, what happens is I get a 12 for my ones digit. I can't have a 12 for a single digit. That's a double-digit number. So really, 1 is the solution, and it's the only solution possible. Sometimes when we start a problem, we think, how am I supposed to know? There's got to be a bunch of options. But the truth is, many times the options are limited. We just have to find what is the limiting factor. The limiting factor here in this problem, the thing that limits us, is the fact that we have to have a single-digit number in that spot. The second problem is very similar. Again, a 3-digit number. This time the digits are going to add up to 13. The hundreds digit is 3 times the tens digit. The tens digit is 3 times the ones digit. Okay. Now, if I had a 0 in the ones digit, the problem is if I multiply everything by 3, I still get 0, and so certainly those do not add up to 13. If I put a 1 in the ones place, and then I do 3 times that and 3 times that, what I actually have right off the bat is a number that adds up to 13. When you did that, did you make a 10? 9 and 1 make 10, and 3 extra make 13. But notice again, we have the same problem or the same situation. If I put a 2 in the first place and I triple it, and I try to triple it again, then I'm trying to put an 18 in as 1 digit in a 3-digit number. And that would never do. So 931 is the correct answer. It meets all the criteria that they gave us. Number 3 is another very common kind of a math problem that we want to make sure we understand how to solve and why it's this way. These kind of things come up a lot, even on standardized tests. So we have a train tunnel. Here's the beginning of the tunnel, here's the end of the tunnel, and I'm told that there are 6 signal lights spaced throughout. They're 20 meters apart. So between the first and second light, it's 20 meters. On through there, it's 20 meters. Each of these is 20 meters. And here's what is not intuitive about this problem. If I have 6 lights, the intuitive answer is to say 6 times 20 is 120 meters. But what we find out is I actually only have 5 distances between them. So I have 5 20-meter spaces. So there is 100 meters from start to finish. The tunnel is 100 meters long. And getting used to the fact that when you're using the beginning and the ending and counting the space in between, there are one less space as there are, in this case, signal lights. So that's a good fact to remember. It comes up many times on word problems.